talk about a research project. And so this is a little bit different from the panel, which was clearly talking about big projects. These are a small project, but I think there's some interesting lessons. So the question that I'm actually interested in is the last one of the panel's topics, which is what is really the edge going to look like, right? And so everybody knows, of course, it's 5G, at least for a little while, and then we'll switch to 6G, I assume. But this is a picture that I use in class and so on. It basically tells us something. It's from an ITU document that kind of has an performance goals and so on. But basically what it does is it basically identifies specific metrics such as peak data rates, the user experience data rates, which are also important, and then also latency, which we know is the kind of historically been a sore point for cellular, but is obviously getting better, as we know. And so on the other side, the research community and also industry already has realized that edge clouds has a big advantage if you want to do if you want to use clouds for applications that have low latency requirements. Okay, and so because you basically bring the computing to the user rather than having the user send its data to a far away computer. So what we're going to look at here is a question of vehicular edge offloading as a way to just kind of look at where there might be problems remaining when we try to deploy offloading in general onto an infrastructure that includes 5G type of networks, not specifically 5G, but networks that have goals and some level of indications that they can offer low latency and high bandwidth performance, and also the impact of edge computing in that domain. And so this is the focus here is going to be the sensor-driven applications, such as some of the things that are associated with autonomous driving, but it's not specific to autonomous driving at all, and low latency constraints. So, as I said, application, sensor inputs, and generating input for a user, which can be a human, interactive applications, or another application that uses the input. I'm going to talk about two classes of applications that differ in what type of state they deal with, and I'll explain exactly what I mean by this when I talk about the application. It's a little bit easier, and I'll talk about two classes of applications. I'm going to skip a lot of the details given the lateness of the hour, but when you're looking, if you're looking at applications that run on the vehicle, there are basically three ways to realize these applications and make them happen. The first one is you execute it on the vehicle. The second one is you take the inputs, send it to the cloud or an edge cloud and get the result back. So you're basically picking a place, either the vehicle or the edge cloud. The third one is partitioning. Okay. The first two are perfectly reasonable for a large number of applications, but for some applications that have high volume sensor inputs, you also run into the problem that communication latencies, not the RTT, but time to send data, is in fact a big factor in the response time to the application. Okay, and in those cases, you may in fact have to do partitioning of the application, where you run part of the application on the vehicle, part of it in the cloud, and that's the case that I will focus on. Collaborators, this actually is a project that was done jointly with General Motors. So we kind of have a car manufacturer's view on this, which is actually a little bit different from what we have in the room, I think. And then I have a bunch of talented people who worked on this and who did a lot of heavy lifting. One of the reasons why General Motors told me that they are interested in this type of project, which is obviously not mainstream for a car manufacturer, is actually very simple. The idea of putting giant computers in cars is not exactly attractive to them. It's expensive, okay? And so being able to offload is a big advantage to them, potentially, if it is possible. There's a second reason, which hasn't come up yet. According to my collaborators at GM, the average lifetime of a car, including second-hand market, is 2 to 15 years. In other words, you can't look at the road and see only 2022 car models. That's not how it works. There are cars on the road that are 10 plus years older. So you're going to have a very diverse set of vehicles on the road in terms of computing capabilities. And that's scary to them, okay? All right, so I'm going to start with something very simple. There is a class of application called data analytics applications. So it takes a sensor input, in this simple example, it's video, and it just needs to analyze the sensor input and come up with a simple answer. This particular application is very simple. You want to have a driver be driving. They don't like the song on the radio or on their that they are playing from their phone. And what they, instead of taking their eyes off the road and pushing some buttons somewhere, they just want to be able to do this to indicate to the car that they don't want to hear this song. Okay, so what happens is basically you have a pipeline of processing going through, starting with a camera feed that records that you're going like this, and then the answer that pops out is switch to the next song. Okay, that's basically what it is. It turns out there are many applications in this category, and they share the same structure that I have here. There are two features that are interesting. The first one is, if you look at the amount of data that is being passed by the stages, between the stages, it shrinks as you move down the pipeline. It shrinks very quickly. Okay, so that is really good because this suggests that offloading is potentially a possibility in the sense that doing it all on the car is probably not desirable because you're sending a lot of data to the cloud or the edge cloud, and so maybe some degree of offloading is needed. The second one shows another advantage of offloading, which is that it's to be expected that if you have a real edge cloud, okay, that it's going to have more powerful computers and servers than what you have sitting in your car. And so by offloading, another benefit is that you get faster execution times. On the other hand, if you have to wait forever for the network to deliver the data, then you've lost all those benefits. Okay, so that's kind of the key idea. So it turns out, and I'm not going to go into the details, but it turns out this is a very easy application to offload. You basically have some estimate of your CPU cycles available, of the network bandwidth available, and you can decide which modules to do locally and which ones to execute in the cloud. That will give you the best and quickest response time. It's fairly straightforward because this very simple structure of the application. And so Ashwin, who did this work, so he worked on this, did this for a bunch of applications, and showed a bunch of other properties. This actually shows some results. Don't have too much time to talk about these, but one thing that I do want to point out is that he basically ran experiments driving around in a real car, waving his hands. Okay, and so you're seeing here the results. The darkest color here is if you execute it locally on the vehicle. So that's a less powerful computer. So that turns out to be problematic. This is when he was driving the car in areas where there was a 4G connectivity. Okay, so this research was about 5 years ago, and so what you're seeing is that you get a nice benefit over the local execution, but then when you're in this is the 3G connectivity. But then when you're in 4G connectivity, you immediately get a bump already because the communication costs are lower. So what the cellular network does is relevant. Okay, it impacts application performance. So that's good, right? So 5G should make this even better, is the short answer. Okay, so now we're going to switch. So the reason why this turned out to be very simple is that in most cases, if you can offload, the amount of state that the application has that has to be transferred to the edge is small. That's why this works very well. So next, GM kind of really surprised me by suggesting that we work on a different application. There's something called SLAM. Now, I'm not sure we have too many robotics people in the room, but SLAM is basically a very different type of application. What it basically does is if you're moving around like driving or walking, and you have a camera, stereo camera in our case, that looks forward, what it does is it continuously calculates your current location and which direction you're heading. Okay? And so the way it does that is by using stereo vision or LiDAR. to basically compare the frames in the video and to see how particular features, so easy to recognize boxes of pixels, how they shift in the frame over time, and then you basically do triangulation based on that to localize yourself, okay, and to change your identify which direction you're heading. So the details of this work aren't really all that important, but this is basically the application that they chose. So stereo vision. So you basically have a stereo video stream. So that's a fair bit of bandwidth. And response time matters if you would use this for autonomous driving. Okay. So this is basically what we did. So the goals here are that we had a existing open source SLAM implementation called OrbSLAM. And our goal was to basically find a way of distributing this so that we get a performance that is hopefully almost as good as the monolithic version that you would run on a server. Okay, that was basically our goal. So so our goal is not to improve SLAM. Our goal is to basically distribute it and not lose too much in performance. So I'm going to give you a very brief overview of how this works. But basically the way this works is that there are basically successive frames are used for localization. The way I described it, you see how the little features in the video frame move around and use triangulation to localize yourself. This is called tracking. This is very efficient. It's very fast, but it is subject to drift, which can be quite significant over time. Then there's a number of optimizations that can be performed. One that is especially important is something that is called loop closing. And how it does it doesn't really matter, but the key idea is important. Imagine that I leave my garage to go to work to CMU. I use SLAM while doing this, and then I turn around, and in the evening I go back home. By the time I get home, I know for a fact that I'm physically in the same location as where I started. Okay. The problem is that due to the drift, this is not exactly where SLAM may think I am, right? If this is where I started, due to continuous drift, SLAM may actually think I'm here, which is clearly very wrong and very dangerous, okay, if you would use that output. So what it basically does is it does an optimization where it says, look, we're going to just use the fact that we know where we started, and so we're basically going to move this point over here, and all the intermediate points on the curve, on the trajectory, are basically adjusted, and you effectively distribute the error that you have across all the points on the trajectory. That's how this works. Now, it turns out this is a little bit late because you're already back in your garage, but this information is stored in a large database of pre-stripped data that now can be used by SLAM to optimize any new and future trips. Okay. The main point I want you to take away is one thing. Having access to this previous strip data is very important for accuracy because it really, really, really brings the drift down to very, very little. It adjusts for it continuously. That's the only takeaway for this. Okay. The drawback, you have a very large pool of data that you need to have access to execute SLAM. That's the drawback. Okay, so now we want to partition this. So we ended up doing some benchmarking. It turns out tracking is very fast. It's done for every frame. And so this is obviously something you want to do on the car. Okay, so this is kind of a no-brainer. The local mapping is something that looks at groups of frames. And so it's a little bit slower and takes a little bit more compute cycles. Okay, but it is actually quite important that you do that because it does already initially help with drift. And then finally, loop closing here is not the actually loop closing itself, but it is using the large database of previous strip data. Okay, and that's not done for that's not used for every frame. That is only used periodically. And so that's actually much more expensive. And you see kind of the whisker plot here. It's hard to predict how long that's going to take. Okay, so that's kind of what we have. So based on this results, we decided to basically execute tracking and local mapping on the vehicle and to do the use of the large database of in the cloud, or an edge cloud, so that we basically don't have to do this heavy processing on the vehicle. So here's what we end up with. Remote mapping, which is effectively a new module that uses a bunch of optimizations, but primarily uses the previous trip data in the cloud at the top of the picture on the right, and then we basically have tracking and local mapping on this. Now here's the question: where do I store this map? Okay, because it turns out that the way SLAM works, there's supposed to be this large database with all the data in it that is being used by all the modules in the system. So large database, okay? And so where are we going to keep this now? Because given that we've partitioned our application. So there's a strong argument to be made that, the previous trip data should be stored in the cloud, because that's where the remote mapping happens that uses the previous trip data. Okay, that seems pretty obvious. The current trip data is being used on the car and is being generated on the car. So obviously you'll keep that on the car. And now the obvious problem is that the whole point of having the previous trip data is that it is combined with the current data from the current trip, all together nicely integrated. But if you keep it on two different computers, that obviously isn't happening. Okay, so the question is, how do you deal with that? Okay, we need a big single shared map. And the answer is, and this is where I'm going to go very heavy on the skipping details. It turns out we moved ahead with two maps anyway, because there is no other way to solve this problem. The data structures are very complicated. Any existing work on consistency between two computers of data completely does not apply here. Okay, so we actually have two maps. We have the local map, which is on the vehicle, and it only contains information collected on this trip. Okay. And then we have a global map, which includes the previous trip data, which is only stored in the cloud, which is kind of the decision that is forced on us. So the question is, how do we actually make this integration works? The way it works is the following. Well, I'm not sure I want to walk that far, but if you look at the right of the figure there, some of the frames that are collected from the current trip are in fact being sent to the cloud, but it is a small subset of the frames. And oh, okay, we have a mouse. Oh, maybe we have a mouse. Oh, here's the mouse. Okay, so some subset of the frames is being sent from the vehicle to the cloud. And then what the cloud will do is it will take these frames, and we're talking maybe 1 out of 10, maybe 1 out of 15, 1 out of 20, very small percentage. And it takes these frames and it basically uses it to localize and calculate the pose, which is the location and the direction of the vehicle, using the previous trip data. Okay. While doing that, it also takes that information and integrated it, merges it with the previous trip data. Then it basically comes up with its definition of the pose, its decision on what the pose is, and it sends this back to the vehicle, okay, over here. And then what effectively happens is that the car gets this and it says, look, according to the cloud, okay, or the version of the remote mapping module on the cloud, I need to be in location X, which is based on previous trip data and should have high accuracy. It compares it with its estimate of the location, and it always discovers they're not the same. What it does is it accepts the location provided by the cloud because it's based on accurate previous trip data, and it adjusts its entire data structure to account for the error. So it okay, so it basically periodically gets some feedback from the cloud. You're off by this much, and then it adjusts its data structure. So it effectively learns from the previous trip data that exists in the cloud. Okay, so this may sound like magic, but this is actually works. And so the key issue here, of course, is now, okay, good. We have this working. And now what's the performance of this going to be in a real system? Okay, so that's what I'm building up to. I'm going to skip this. I have just one set of results here that shows how this works. I'm just going to pick one of them. There's a bunch of optimizations that are not really crucial, so I'll skip those. But here, what you're basically seeing is this is the frequency with which you send frames up, let's say every 10 seconds here, every 20, etc. And what you're seeing is if you send up the frames very, very frequently, like here, you actually get a very relatively small error here, about 1 meter, okay, relative to the what the monolithic SLAM does. The problem is you're sending a lot of data, okay, which is the red bar here. And then as you increase the period, okay, you're seeing that the error goes up, but that obviously the amount of data that you use goes down. Okay, so you get exactly the result that you want. One of the things I want to point out, in practice, we don't use a fixed period. We adjust the period over time based on various things. So if in reality, the period is not fixed. Okay, so now I'm moving on to the question that is really the more interesting one is, what did we learn from this other than, we can actually parallelize SLAM? So I want to get back to this and kind of see how latency and network performance comes into play here. So this is a graph from the paper that Kwame put together. And so what it shows on the right, and this is a little bit hard to read, but again, there are two y-axes. There's one on the left and one on the right. The one on the left is basically what I call latency, okay? The latency here is effectively the response time. So when I send up a frame from the vehicle to the cloud, how long does it take before I get the response? That's an important number because in that time window, the car is using the wrong pose information. Okay, so this is an important number. So what we're seeing here is then that time goes up, and the x-axis is the round trip time. Okay, this is artificially generated. Obviously, we go a little bit high with 400 milliseconds, and certainly with 5G, obviously you're in the wrong order of magnitude there. But so what you're seeing is that as the round trip time goes up, the response time goes up. The white part of the bar is effectively the compute time, okay, and the pink part of the time is effectively the communication time, the time that you're waiting because the network is sending bits either one way or the other, way up, okay? And so what you're seeing is that the response time here of, or how long you have to wait to get a correction to your current pose is actually depends fairly strongly on the RTT, which is highly surprising, you would guess, but it's actually quite an increase, okay? And so we use different strategies, but the results are consistent. Okay. Now here's an interesting thing. This is not using 5G at all. Okay. This is we're just running this over an Ethernet, a 1 gigabit Ethernet link, with literally the two computers, the server that represents the cloud and the laptop that represents the vehicle. They're just literally in the same room. Okay. So we could potentially go as fast as a gigabit on this line. So the question that I'm going to ask is, how is it honestly possible that to send one frame, which is 0.5 megabyte in this case, this is a very old sensor input we're using, takes 1 second to send from a laptop to a computer at a link that supports hundreds of megabits per second? That is just really bizarre result. Okay, so how is that possible? Because obviously, I think a gigabit Ethernet line is going to be faster than 5G in terms of latency, right? And now we're obviously adding artificial latency here, but it has more bandwidth than what your average user can expect in 5G. So, okay, so let's go look at this. So we looked at this and considered the fact that in reality, what we have been working on is an application, but the Ethernet cable is way at the bottom of the stack, right? And so the unfortunate thing is that what the application observes is not just the Ethernet cable in our case, or 5G and for the scenarios we've been discussing here, but it also observes all the stuff in the middle. that also impacts the performance of the network because the network is the entire protocol stack. Okay, so let's look at this in a little bit more detail. So SLAM, 5G, and so we have all these layers in between. And so when we started to look at this, what we saw was that there's a little bit of a disconnect between what applications people care about and network people care about. Okay, and so I actually consider myself a networking person, so I'm kind of in the wrong here as well. So applications care a lot about something called flow completion time. So let me first explain the graph. In this particular scenario, what we have is we're basically sending a request, which is a video frame. Okay, so that's a large block of data. And then there's computing going on here. And then there's a response that is sent back, which is actually quite small. So this is not exactly to scale here. This is what the networking people call the flow completion time. It's basically from when you send the first bit until you receive the last bit of this particular transfer of data. The flow completion time here is for a 0.5 megabyte video frame, which is not a lot of data, let's be honest. Okay. So it turns out that what you saw in pink in the previous graph is this, the time to send the video frame. Okay. And it was quite substantial. So what we're seeing here is that from an application perspective, they actually care about the response time, but the flow completion time can make up a substantial part of that. Okay. If you then, okay, so that's what the application people care about. Networking people, they care about packets. Networking people don't care about flow completion time. They care about packets, okay? And so if you would actually ask the application people, you know, what about packets? Do you care about their performance? And then they go, no, we don't care about that. We care about the flow completion time. So for those of you who are, you know, look at networking above the 5G layer, what networking people talk about is things like having applications that send packet bursts. They are bad applications. Applications have to do packet pacing. They have to spread out their packets over time, send at a constant bit rate, and so on. TCP fairness, a big topic in the research community right now, and it has been for a long time. The focus is on packet level fairness. Okay, so those are the some of the kind of the gap that I'm talking about between what networking people and application people care about. So let's talk a little bit about the different layers, and I'm going to keep this very quick. The first one that I want to focus on is actually the IP layer. But the same is to some lesser degree true for data link, but one layer is bad enough. So let's basically look at flow completion time given a model that would be an idealized view of how protocols such as the IP protocol should work. Okay, so basically what they will do is the following. I'll explain this colorful picture here. I have 3 applications sending a flow, sending data from, let's say, Pittsburgh to Porto or Aveiro. Okay, and so there's a brown application, a blue one, and a green one. So what's really happening here is that if you're looking at this is basically the first packet. This is basically, oh, sorry, this is the first packet that is being sent. And we have nicely interleaved the packets of the different applications because we want to be fair to the application and give them equal bandwidth. Okay, packet level fairness. So what I have is there are 4 packets that make up this particular chunk of data, okay, which is obviously not a lot, but it's all that fits on the slide. And so if I now look at when the application has the entire chunk of data, all 4 packets, well, it's basically going to be here. Oops, this disappeared. It's basically going to be here for a green flow, blue flow, and brown flow. And so what you're seeing here is that you made the flow completion time as high as possible. You've maximized it. Well, that's a little bit odd if you give this to an applications person, because they're going to say, wait a second, this is the wrong thing to do. We want to have this go down. Okay. And so if we do flow completion time without interleaving, And we're just kind of pretending that we can do this for now. What you can do is you can say, look, I'm first going to send all the green packets of this particular chunk of data. So the green flow is happy very quickly, the green user. Then I'm going to do blue, and then I'm going to do brown. And what you're seeing is that the average flow completion time has gone down, right? Wait, there's something wrong. Yeah. Hello? Yeah, we're back. So the average flow completion time has gone down. Now you can look, well, what does this mean for fairness though? Well, the good news is that the brown user is no worse off, okay? The brown user didn't lose performance, but the other two users basically benefited, okay? And so the other thing is that if you really want to worry about fairness, maybe you should be worrying about fairness at the chunk data chunk level, not at the packet level. That's kind of ideally what you would like to do. So next time when they send data, the brown user gets to go first and the green user gets to go last. So that would be kind of the ideal scenario. That turns out to be a little bit hard to do in practice, but you know, it's kind of a model. It actually turns out that, oops, what's happening here? Yeah, okay. So it turns out that I didn't discover this problem. This problem has been known for a very long time. In fact, people in data centers worry big time about this, okay? And this is part of the incast problem, which is a well-known problem in data center networking. And so the problem that they're having here is they have a lot of servers sending data to users. And so the flow completion time is very important. You want to see your web page, right? And so if you interleave this data on this link here, you maximize the flow completion time. It's exactly the same problem that we're having and that I discussed earlier. And so it turns out that people have known about this. There's actually a solution for that. You can actually do, there are scheduling algorithms that allow you to kind of control how many flows are being served simultaneously, okay? And so this is used inside data centers. I'm actually not aware of this being used outside of data centers, but maybe it should. And actually, there is actually a recent Cornex paper, which I actually enjoyed reading, which does something somewhat similar in the cellular world. Okay, so it's a little bit of a hard read, although for this audience, it's probably easier than it was for me. Okay, next problem, TCP. Okay, my favorite topic. Why is low RTT important? I'm going to argue first that it is not important at all. TCP is a transport protocol that does reliable packet transmission, okay? And so the way it does is it doesn't send one packet, wait for an ACK, and then send a second packet. It pipelines packets, right? So it basically sends packets over time and it fills a pipeline. So the key idea is if you have something like this here, then going from Pittsburgh to Chicago is obviously a bit faster than going to Vero. And so what's going to happen is that if the available bandwidth on the network is the same in both cases, it's going to send packets at the same rate. Okay, that is what pipelining means. The actual length of the pipeline in terms of latency doesn't matter. So why isn't this working? Well, it turns out that TCP has a little function called congestion control. And so I suspect there are a lot of people in the room who may not be familiar with the details, but you would imagine that the rate of a transmission is controlled through a number that is expressed in packets per second. That is not how it is expressed. It is expressed in packets per round trip time. Okay, and you start with 10 packets per round trip time, and then there's an algorithm that increases this. Now, if you have a low round trip time, then you are going to start at a much higher round trip time than at a much higher data rate than if you have a high round trip time. So to a large extent, the problem here is not fundamental to the network, it's caused by TCP. Okay, so that's actually one of the big reasons why we're seeing this very high delivery rate for higher RTTs. So if you would just run, so basically somehow avoiding this problem is important, and that will allow you to live with somewhat longer RTTs and be a little bit less obsessed by this. Again, it turns out that the data center people have figured one out. And so they are basically very obsessed with latency and very obsessed with not having these long startup times and having the rate increase very slowly. Okay, so there's a lesson again to be learned there. And then I have another link on the wireless layer, but I'm just going to skip this because I'm pretty sure that the physical layer people in the room here are well aware of this. So in the interest of time, I'm going to skip this. So wireless links are always tricky. So this is actually old work. But as I said, I'm going to skip this, except there's a lot of animation. So that's kind of some of the things that we learned, right? So anyway, I don't have too much doubt that 5G and edge computing is going to be the future for the near term. I don't think we need to necessarily focus entirely and limit ourselves to autonomous driving, though. There are other reasons why you might want to do offloading and use edge clouds. Okay. So there's a question of how edge computing, what it will look like. That itself seems to be still a debate. I'm a little bit surprised by that. I personally actually think it's going to be real small data centers that aren't sitting on lampposts, but are actually physically somewhat close to where the action takes place, the applications are running. Okay, and so the real question is in the networking, because the reality is we can't just run applications directly on 5G. We need the stuff in the middle. Okay, and so I think we just need to do something about that. And start to think about the full protocol stack than just the bottom one and the top one, right? I really enjoyed the last part of discussion of the panel, actually, because a big part that comes into play here is what the relationship is between the different parties that exist at the edge. Data center networking people have figured all this stuff out, but they own the servers and they own the data center network, and they have their own implementation of just about everything that they're running there. Okay, they don't just run the stuff that you run in the regular public internet. Okay, that's not what they run. In fact, all large cloud providers have their own private wide area networks. They don't use the public internet that we use for all kinds of stuff. They have specialized wide area networks to cut back on latency. Okay. And so now in the edge, we're not just going to be able to just download a standard Linux release and get good performance. I don't think that's going to work. So looking at the relationship between the different providers is, in fact, I think, a big part of this of the problem. Because yes, historically you have a cellular provider, you have cloud providers, right? You have maybe a service providers that provides autonomous driving services and other services. There's kind of like, well, somebody has to build the car, right? They have to build the sensors. They're not going to be the same in all cars. So there's a lot of players that come into play here, but that's not necessarily my area of research. My focus is on the network. Okay, thank you.
I have a lot of questions about this, but we should make a project about this. But the main, or maybe for mine, these data center networking solutions that you mentioned that solve many of these problems, they are not standardized, as I understand. They don't use standard protocols, as I understood. One thing about the internet is that people agreed on standard protocols that sort of served everybody. So my question is, what would be, can you assess the effort of bringing this, or at least parts of it, to standard, or sorry, to interoperable world?
Yes, I think that's exactly that is a big part of the problem. Actually, I'm glad you pointed out. It is not standardized what they do in data centers, and the problem, of course, is that for the data center operators, like the Googles and the Facebooks and so on, they for them this is one of their areas where they can innovate. Right, that's where they can get an edge. Okay. And so, yes, it's also only runs in their data center. Okay, and so they do crazy stuff. And yes, it is going to be very different, right? The problem is you could standardize it, right? Also, there are, in fact, in the public internet, many versions of TCP available, and they all use different congestion control algorithms, and there are ways of making that particular thing work. It's a little bit limiting because it basically means that the congestion control is entirely done on the sender and without help from the receiver. The big difference, which I think you're implying, and I'll just make it explicit, if you would think of each edge cloud with its wires or wireless links to vehicles as a little data center, that would be nice, right? But if it's then operated by different people running different versions of TCP and you're driving around in your car, well, that's going to get very interesting very quickly, right? So yes, but maybe it should be standardized. But there is a question of, can we effectively not just straightforwardly use what the data center people do, but can we learn from it and then adapt it, because it will have to be adapted.
Then I have another question, which is, this congestion control research, I don't know, holy grail, is driven by this fear of congestion collapse, also by this multiplexing of many flows going back and forth in a fully meshed network. When we think about edge computing, talking to the clients, you do not have a fully meshed network. You have a much more tree-like structure where everybody's probably talking to the same data center. But first, you don't get that. I mean, it doesn't never explode or grow to millions because it's local. So you have this locality issue that Joaquin was talking about earlier. So if we put this local, is then congestion control such a huge problem? And if it's not, do we really need TCP?
Well, I think the reality is, if you look at what they use in some of the data centers, it doesn't look like TCP, right? So the answer is that not necessarily, right? So also, I'm not sure that, so TCP, things like error recovery and so on, these are all probably kind of okay, right? It's really the congestion control that is the big thing. The congestion control that we use today in TCP in the internet is defined on the principle that for every destination, you have no idea what the round trip time is, and you have no idea what the available bandwidth is. If I'm sending to an edge cloud, it looks like I at least have a clue about some of that, right? And so there's certainly some assumptions you can make. And that's also what's actually being used inside data centers. They know the latencies are going to be measured in milliseconds. And really, milliseconds, it's a horrible number for them, right? So I think that you need to look at something. Yes, I think we need to look in that direction. In reality, the cellular network will also be used to access the internet itself or remote clouds or whatever, right? So you really have, maybe you can look at it as two trees that, then, are overlaid on top of each other in the cellular part of the communication, right? And then I know one of the things you're also interested in is what are security issues, right? So the overhead associated with that, given all the parties involved, right? So that is actually another issue.
There's time for additional question.
Sort of answer the question. I was going to ask you, you talk about network, you call yourself a network people. And you said, okay, so it seems like Edge Cloud doesn't work really well with our OSI stack concerning the internet. If you call yourself network people, I was going to ask you, okay, we have the TCP, which will be the transport protocol or UDP, and we'll have the IP protocol stack. Between the both of them, which will be the one that you will focus on for changing concerning this new edge cloud instead of the normal internet network infrastructure? Because of the way you talk, it seems right away that you're going to mention the transport protocol instead of the IP. That's the feedback that I get.
No, I think there's two layers that you really need to work on, right? So the first one is a reliable transport and the congestion control. Okay, you need to work on this. Note, by the way, that I have no problem with the protocol stack by definition, especially if you're going to have a mobile device that talks to a lot of different operators. You need a standardized protocol stack. Okay, so let's be honest about that. So you do need to address, I think, the TCP problem as it exists in the public internet, because it introduces, it really penalizes you for latency too much. And the latencies are not just the 5G part. There is more to the internet than 5G, right? So any kind of queuing that happens anywhere is also going to impact your performance. So that's the first one. The second one is the fact that the kind of trying to interleave as nicely as possible. That's the second one. That is actually something that is easier to manage here, because ultimately that's kind of controlled by the base station, right? It controls who gets to send when on the network. And so it is in the best position. That's actually what the paper I referred to is based on. So it is basically in the position to try to reduce the burstiness. The key idea is very simple. Instead of having 100 cars send data at the same time, kind of say, okay, U5 can go, and then U5 you can go, and U5 you can go, and it has more of a longer term window that it uses to be concerned about fairness. Okay. And so that, I mean, I'm obviously oversimplifying this a lot, right? But those are really the two issues you need to really worry about, because these are latencies that are added on top of whatever 5G has.
Okay, so one last short question.
Okay, so sorry for the late hour. Anyway, so being a completely applications guy, maybe the only one in the room, I'm not sure. So it's more as in a comment than a question, and it's good to see that the network guys are taking that into consideration, because being an application and a roboticist at Seoul, and in this case, the very particular case that you started by presenting, the offloading, and again, a very controversial statement. I don't believe that much in offloading, or in very specific only I'd say critical applications. Although there is some trend of ideas about offloading the control, the actual control of the car, of the vehicle, of the robot, whatever you want. I've heard about that trend. As an application guy, I completely abominate the idea. So what would be but it's good to see that the things are being considered in terms of application level, because as you say, offloading and getting back to the response will take some time. And even the example that you gave about offloading part of the SLAM, the pose adjustment would be based on the past, right? Because in the meantime, in that 1 or 2 seconds,
previous trip data, yes.
Previous
so
data.
Right. So there is an assumption that the drift is on a short time window, the drift is small, right? Mm-hmm. Also, the reality is, and we can argue about the details, and I'm not the right person to actually participate in this argument, but I just asked, right? Okay, a car lane has a certain width, right? In the response time that you have for your pose update, the question in many cases is, have you drifted out of your lane? That's, the question is, how much drift is bad and how much drift is acceptable, right? So you need to respond fast enough so you're not going to be in another lane, okay? That's really simplifying it, but it's a good first order approximation, right? And if cars actually don't, paired with computers, they move fairly slowly, right? I mean, really, okay. And so especially they go fast this way, but this way and this way is a little bit slower. So I understand your concern about the offloading the control of the car, which I interpret as meaning you press the brake pedal and you're going to send a message to the cloud saying, do you really, really, really want me to brake? That sounds like a really bad idea.
Not exactly in that, but even in the processing, the camera sends the image, it's being processed in the cloud, and then the cloud sends the results. So there's a car here, there's a pedestrian there.
No.
On that level.
So the brakes need to work purely entirely on the car, But I understand that. But again, the whole point of being able to use sensors is that you can see that somebody is in the road before maybe the driver can see it. So that gives you a little bit of time to notify the vehicle, right? So I'm not going to say all these problems are solved, but I think there are cases where this is suitable. My bigger concern is that if you have an older car, you don't get this technology. Right. So that's really the concern, right? And, you know, I don't know the answers, right? I was honestly surprised by what we discovered here. Okay. And I'm very familiar with TCP and I'm very familiar with how IP works and the data link layers work. Okay. So, and I was surprised to see how much impact it has. Here's the problem. Most application data that is sent in short flows, which means that where the impact of the latency is the highest. That's the problem. If you send a gigabyte, nobody cares.